all in fifth lecture of biomolecules. Before going to the main course of fifth lecture, I will like to give a recap of lecture 4. In lecture 4, we have discussed about glycoside formations. We have also discussed about its mechanism. We talked about reducing and non-reducing sugar. We talked about anomeric effect, and we discussed about the how do we monitor, how do we measure the blood glucose level in the diabetic patient, that basically what reaction involved over there. These all things we have discussed in lecture 4. And again, continuing with the same part, carbohydrate chemistry. Today I am going to discuss about the reactions of monosaccharides in basic solution. Reactions of monosaccharides in basic solution. What happens to monosaccharides if they are taken in the basic solution? Basically, one chemical phenomena occurs. Under basic condition, they go for epimerization. So now I am introducing the term epimerization. Let me define epimerization. What is epimerization? In a basic solution, a monosaccharide is converted to a mixture of polyhydroxy aldehydes and polyhydroxy ketones. Polyhydroxy aldehydes and polyhydroxy ketones. How does it happen? Let us look at the mechanistic parts, that what happens to D-glucose if it is treated with the base, and what kind of chemistry takes place. So, I am going to draw a structure of D-glucose. So, this is D-glucose, D-glucose is getting treated with the base, as I told you under basic condition. So, here I am taking base. In presence of base, base will abstract this proton at the alpha position to the carbonyl, and that converts it to the C2 epimer. So, it will abstract proton and it will form H2O, and it will get converted to innovate, corresponding innovate. So, this is the enolate ion, Now, this enolate ion can again go back in presence of water molecule, it can go for reprotonation. So, this is the C2 position. C2 position under basic condition, abstraction of proton is taking place and it forms the enolate ion. Again this enolate ion, now this is sp2 hybridized this carbon, and it can go back again for the reprotonation if this lone pair pushes back. Now two possibility exist over here. One is the either from the top phase protonation can take place, and other this protonation can take place from the bottom phase. So, if it is taking place from the bottom phase, then it will generate another molecule, another aldehyde, and this is another aldohexoses D-mannose, plus hydroxyl group will be there as a side product. So, what happens in this base catalyzed epimerization? Let me again repeat it. This base catalyzed epimerization. First thing, base removes a proton from the alpha carbon, forming an enolate ion. Notice that C2 in the enolate ion is no longer an asymmetric center, because this it has been converted from sp3 to sp2 hybridized center. So, it is no longer asymmetric center. Now, when this C2 is getting reprotonated, the proton can come from the top phase, or it can come from the bottom phase, forming both D-glucose and D-mannose. If it is coming from the top phase, then it will form D-glucose, and if it is coming from the bottom phase, then it will form D-mannose. D-mannose, this is the C2 epimer, C2 epimer. This is C2 epimer. So, we saw that in presence of base, an aldohexose can epimerize to another aldohexose. Basically, the second position stereo center gets degenerated, and from sp3 hybridized carbon to it get converted to sp2 hybridized carbon, and again after the reprotonation of the enolate ion, that generates the mixture of aldohexoses, where the other compound is epimeric at the two position of the same what the starting material we had. In case of D-glucose, under basic condition, it can lead to the mixture of D-glucose and the C2 epimer D-mannose through the discussed mechanism. Now, I will discuss about this epimerization in detail, particularly this rearrangement process, that how is it happening. Basically, if you see, we had one fixed stereochemistry at the C2 position, and we degenerated that C2 position to the sp2 hybridized center, and then again by the reprotonation we have generated a mixture, since these all transformations are in equilibrium. So, let us discuss indiol rearrangement. Indiol rearrangement. What happens that during this process, what the epimerization I just discussed, in addition to forming its C2 primer in a basic solution, D-glucose also undergoes an indiol rearrangement which forms D-fructose. So, in addition to forming its C2 epimer in a basic solution, D-glucose also undergoes an indiol rearrangement. An indiol rearrangement which forms D-fructose. Which forms D-fructose. How does it form D-fructose? D-glucose, how does it form D-fructose? And subsequent, again this D-fructose can further go for the subsequent indiol rearrangement to form the other ketohexoses, because D-fructose is ketohexose. Again it can go under the basic condition for the subsequent indiol rearrangement to form the other ketohexoses, and that way the carbonyl group will keep on traveling across the chain. So, let me explain that indiol rearrangement. I will start with the D-glucose. D-glucose reacts with the base, as we saw in the case of epimerization, to form enolate ion. Enolate ion. Now, this enolate ion can go for again protonation with the water molecule, and that will give corresponding indiol. So, this is indiol forms as an intermediate, indiol. Now, this indiol can again, what the hydroxyl group is there in the reaction mixture, can go for the deprotonation and it will generate the enolate ion again. enolate ion. Now, this enolate ion can go for the protonation. Again, this negative charge will push and it will go for the protonation. Plus. So, again that protonation will take place from water molecule. So, water molecule is there which will generate hydroxyl. It will give D-fructose. Let me explain it again, this whole reaction process. Base removes a proton from an alpha carbon forming an enolate ion. Now, this enolate either C2 can be, if we push this lone pair, then it can go for the further protonation at the C2 position to generate the D glucose and its epimer, or if it gets protonated, it forms indiol. Now, this indiol has two hydroxyl group. It has two hydroxyl group. Now, if deprotonation of the first hydroxyl group is taking place, then again it's end up in going to the D glucose or D mannose. If deprotonation of the second hydroxyl group of the indiol is taking place, it will generate D fructose after the tautomerization. Another indiol rearrangement basically again push the carbonyl group one carbon down. As we saw that we started with the aldohexoses and we end up with the ketohexoses, and again if we do indiol rearrangement with this D fructose with the same sequence of reaction, again carbonyl group can move further one carbon down. To understand in a better way this indiol rearrangement, I will take one problem. So, let us solve a problem. When D-tagatose is added to a basic aqueous solution, an equilibrium mixture of monosaccharides is obtained. Equilibrium mixture of monosaccharide is obtained, two of which are aldohexoses. And two of which are ketohexoses. Identify the aldohexoses and ketohexoses. Now, identify aldohexoses and ketohexoses. So, our job is to identify the aldohexoses and ketohexoses what forms from the D-tagatose. Now, I will write the structure of D-tagatose. So, let us take D-tagatose, ketohexose, basically D-tagatose. If you remember classification of monosaccharides, I have discussed this structure over there. All right, so I will number it here to make it more apparent. 2, 3, 4, 5, 6. Now, under basic condition, what will happen that again alpha to the carbonyl proton abstraction will take place and that will get converted to indiol. Indiol. So, I am writing here indiol. Now, it has two alpha position. One alpha position is carbon number 1 and other alpha position is carbon number 3. So, here I am abstracting carbon number 3 proton and converting into indiol. Now, this asymmetric center has been degenerated. Now, again if indiol rearrangement is taking place under basic condition, two possibility exist over here. If abstraction of this proton is taking place, then it will get converted to hexoses with the mixture of that where the protonation can take place from the top face or protonation can take place from the bottom face. So, two stereoisomer will get generated. Let me write those two stereoisomer. One this one and in other where hydroxyl group is right hand side. So, this is D-tagatose. We got the same starting material after the epimerization. Same starting material, we got the mixture with same starting material D-tagatose and D-sorbose. So, this is D-tagatose and this is D-sorbose. This happens if deprotonation is taking place at the third position. If deprotonation takes place at the first position, if attack, so I will attack at the C1, attack at C1, here attack at C3, base attack at C3. So, attack at C1, So, base will abstract this proton and it will form enolate. Now, enolate is formed. Now, this enolate can again go for the protonation. This can go for protonation to form indiol. Again indiol is formed and this indiol will again go for the deprotonation and this deprotonation of the hydroxyl OH leads to the aldose formation followed by protonation at the C2 position. Now, again protonation can happen from both the faces, from the top face or from the bottom face. If it happens from both face, that will lead to the two corresponding stereoisomers of the aldohexoses. So, this is D-talose, D-talose, and in the other case so if from the bottom face then D-talose, and if from the top face then it will form D-galactose. So, another D-galactose. So, we started with the D-tagatose and we end up in the with the mixture of D-tagatose, D-sorbose, D-talose and D-galactose, D-galactose. So, basically we got the two aldoses and aldohexoses and two ketohexoses through this reaction, and in totality what is happening, basically it is a indiol rearrangement through the scaffold is taking place, where again deprotonation and reprotonation is happening through this process. And what did we observe? That in the D tagatose, where carbonyl is at the 2 position, it is getting transferred either upside, or it can get transferred at the downside. If it gets downside, then it can travel again across the chain, and if it travels upside, then it can get converted, ketose can get converted to aldose. So that's a very good example to understand. So if you treat the D tagatose to a basic aqueous solution, equilibrium of monosaccharide will have various aldohexoses and ketohexoses. Now let's talk about the reactions of these monosaccharides, particularly oxidation reductions of monosaccharide. Oxidation reduction reactions of monosaccharide. Oxidation reduction reactions of monosaccharides. Since monosaccharides contain alcohol functional groups and aldehyde or ketone, the chemistry delivered by monosaccharide should be the transformations of corresponding groups, transformation of hydroxyl group, transformation of ketone group, transformation of aldehyde group, and the reactions of monosaccharide can be classified in a way that this can react. If it is aldose, then it should react with the nucleophile. If it is ketose, then it should react with the nucleophile. And if it is hydroxyl, then again it can give the required transformation, whatever the alcohol groups gives. So let's take first reduction reaction. So here I am taking D-mannose, which is aldohexoses, and I am treating it with the reducing agent. Reducing agent is here sodium borohydride, D-mannose. Reduction by sodium borohydride will convert aldehyde into alcohol, and it will form primary alcohol. Aldehyde will get converted to primary alcohol. It will generate, after the reduction, D-mannitol. Mannose will generate D-mannitol. D-mannitol and LD-tol. Since it has been derived from aldehyde, it is also known as an LD-tol. If you start with the D-fructose, again sodium borohydride, here also protonating agent is needed, and I have hydronium, that acid reagent is needed. Again, if you do sodium borohydride reduction, and the second is hydronium species. Now, since this carbonyl can get attacked from the top face by the hydride ion, or it can get attacked from the bottom face. If it get attacked from the bottom face, then it will give glucital, but if it gets attacked from the top face, then it will give mannitol. It will generate two stereoisomers. So, if it is getting attacked from the bottom face, then it will generate D-mannitol, but if it gets attacked from the top face. So, again sodium borohydride, and second is hydronium species, that will give reduced compound, where hydroxyl is at the right side. So, this will give D-glucitol, D-glucitol. Now, what is difference between D-mannitol and only the orientation of hydroxyl group? In one case it is left, in the case of D-mannitol it is left hand side, and in the other case it is right hand side, if you see. So, by the ketohexoses reduction, we are getting mixture of the two alcohol, D-mannitol and D-glucitol. This is also an LD-tol. D-glucitol, also called sorbitol. D-glucitol, also called sorbitol, is about 60% as sweet as sucrose. It is found in plums, pears, cherries and berries. Cherries and berries. It is a 60% as sweet as sucrose. Now, let us talk about the oxidation reaction. So, we discussed reduction. In the reduction, we saw that mannose can get reduced to the mannitol, whereas if we start with the ketohexose D-fructose, it will give a mixture of the product. If the hydride will attack from the top face, then it will give D-glucitol. If it attack from the bottom face, then it will give D-mannitol. These two products are possible. Now, let us talk about the oxidation. D-glucose, after the oxidation, generates D-gluconic acid. What is the structure of D-gluconic acid that can be easily generated from the D-glucose. D-glucose in presence of bromine water gets converted to aldehyde group, gets oxidized to the carboxylic group, and it gives D-gluconic, as well as it generates bromide ion in the reaction mixture, which is colorless. So, how can we figure out that oxidation reaction has been completed? If we take D-glucose and treat it with the bromine water, it will bromine water which is basically reddish brown in color because of the color of bromine, and after the reaction basically aldehyde group will get converted to acid, it will form the D-gluconic acid, and it will generate bromide ion. So, the reddish brown color of bromine after the oxidation of monosaccharide glucose to the gluconic acid will, because of it gets converted to the bromide, will disappear, it will become colorless. Basically bromide is getting reduced, bromine is getting reduced to bromide and glucose is getting oxidized to gluconic acid. Both aldose and ketoses are oxidized to aldonic acid. So, if you take both aldoses and ketoses are oxidized to aldonic acid by Tollens reagent. What is Tollens reagent? Ammonical silver nitrate, Ag plus, NH3 and OH. Ammonical silver nitrate is what we say basically the mixture contains. So, first we discussed about the oxidation of glucose with the bromine water, where it gets converted to gluconic acid, where only aldohexoses has been converted. However, if we want to convert both aldoses and ketoses, if we treat with the Tollens reagent, they get oxidized to the aldonic acid. So, let me write the structure. I am writing here representative structure for the ketoses. Ketose under basic, since the Tollens reagent is having ammonical silver nitrates, basically it has base also and Ag plus is there. So, under basic condition, as we discussed that it can go for indiol rearrangement, and because of the indiol rearrangement it will get ketose can get converted to aldose, basically ketose can get converted to aldose. So, it will form aldose. Now, this aldose in presence of Ag plus and ammonia can get converted to carboxylate ion by the oxidation of aldehyde to carboxylic group. That is why tolerance reagent can oxidize aldoses and ketoses. Plus silver is 0 forms. The oxidizing agent in tolerance reagent is Ag plus. It is reduced to the metallic silver. It is getting reduced to the metallic silver Ag 0 that forms on the inside of the test tube when we do reaction. Basically, when we treat aldose and ketose with the ammonical silver nitrate, which is basically basic in nature. So, what happens that aldose gets converted to corresponding aldose, and then Ag plus oxidizes it to the carboxylic group. Aldehyde gets converted to the carboxylic group, and that is the reason it can oxidize both aldose and ketose, because under basic condition all the ketose gets converted to the aldose. So, the oxidizing agent in tolerance reagent is is silver plus. It is reduced to, which gets reduced to Ag metallic silver, basically forms metallic silver, which gets deposited on the test tube wall. Although tolerance reagent only oxidized aldehyde, it can be used to distinguish aldose and ketose. The oxidation reaction is carried out in a basic solution that will convert a ketose to an aldose by an Indiol arrangement, and the aldose will then be oxidized by tolerance reagent. So, again I am repeating, although tolerance reagent only oxidizes aldehyde, it cannot be used as a distinguishing reagent between the aldose and ketose, because it requires basic reaction condition, and basic reaction condition will convert ketoses to aldoses, and then again aldose will get oxidized to the corresponding aldonic acid. Now, I will introduce another final oxidizing reaction, the oxidation reaction in presence of nitric acid. In presence of nitric acid, it converts even primary alcohol to the carboxylic acid, and the aldehyde group also gets converted to carboxylic group. So, it gets converted to dicarboxylic acid, D-glucaric acid. D-glucaric acid and aldaric acid. Dilute nitric acid is a stronger oxidizing agent, and it oxidizes aldehyde group to carboxylic group as well as the primary alcohol group to the carboxylic group. It does not touch the secondary hydroxy group. If you see that this polyhydroxyaldehyde is having multiple secondary hydroxy group, but it does not touch. Only the primary alcohol group is getting oxidized to the carboxylic group, and aldehyde group is getting oxidized to the carboxylic group. It forms D-glucaric acid. So, now I will stop here. To conclude, we have discussed about the different reactions of a monosaccharide in basic condition, and there we talk about epimerization, we talk about indiol rearrangement, we also talk about different indiol related problems, that how a ketose can be converted to the mixture of aldose and ketose under if it is kept under basic condition by taking the D-tagatose problem. We have also discussed about the reduction reaction of monosaccharide, and we saw that how aldehyde can be converted to the primary alcohol, whereas ketose in the case of aldose, it will get the corresponding primary alcohol D-mannitol if we start with the aldohexose. However, if we start with the ketohexose, that will give mixture, because that they are the carbonyl of the ketose will get attacked from the bottom face or from the top face, and that will give the corresponding alcohols, secondary alcohols, by the reduction of the ketonic group. We have also talked about the oxidation, and oxidation we discussed that how oxidation with the bromine will lead to the of the aldoses to the aldonic acid. If we take aldohexoses, that will form the aldonic acid. However, if we take ketoses, treat them with the tolerance reagent, that oxidizing reagent, that will also get oxidized to the aldonic acid, because the tolerance reagent has a basic ammonical silver nitrate, and there the oxidizing agent is silver plus. However, because of the presence of the basic condition, the ketose can get converted to the aldose, and that aldose forms the aldonic acid. Tolerance reagent can also oxidize aldoses to the aldonic acid. So, tolerance reagent can oxidize both aldoses and ketoses. The one important point here is that we cannot use tolerance reagent as a distinguishing oxidizing reagent between the aldose and ketoses, because it oxidizes both. Also, the aldoses can be oxidized by the dilute nitric acid, and there we can get dicarboxylic acid. The aldehyde group of the aldohexoses get oxidized to the carboxylic group, and the primary alcohol group gets oxidized to the carboxylic group, and that generates the glucaric acid. If we start with the glucose, it forms the D-glucaric acid. However, the secondary hydroxyl group does not get oxidized. Now, I will stop here. We will again continue with the carbohydrate chemistry in the next class. Thank you very much.